Narrator voiceover. Ever wondered how AI models like GPT or BERT understand language so remarkably well? The answer lies in a revolutionary architecture called the transformer. Today, we're diving deep into the technical heart of transformers, exploring how self-attention mechanisms, positional encoding, and layered neural networks enable these models to process language with unprecedented efficiency. Whether you're a researcher, developer, or just curious about AI, this video will unpack the math, the theory, and the real-world impact of one of the most influential innovations in machine learning. Section 1. The problem with RNNs and the birth of transformers. Before transformers, recurrent neural networks, RNNs, and their variants like LSTMs dominated natural language processing. But RNNs had a critical flaw. They processed text sequentially, which made them slow and prone to vanishing gradients when handling long-range dependencies. Imagine trying to understand a 1,000-word essay by only seeing one sentence at a time. That's the challenge RNNs faced. Enter the transformer, introduced in 2017 by Google researchers. This model abandoned recurrence entirely, replacing it with a self-attention mechanism that could process entire sequences in parallel. The result? A massive leap in performance and scalability. But how does it actually work? Section 2. Self-attention mechanisms, the core innovation. Let's break down self-attention, the star of the transformer show. At its core, self-attention allows the model to weigh the importance of different words in a sentence relative to each other. For example, in the sentence, "the cat sat on the mat," the model learns that cat and sat are more closely related than cat and mat. Here's the math. For each word, the model generates 3 vectors, queries, keys, and values, using learned weight matrices. The attention score between 2 words is calculated as the dot product of their query and key vectors, scaled by the square root of the key dimension. This score is then passed through a softmax function to produce weights, which are multiplied by the corresponding value vectors to produce the final output. But this is just the basics. Modern transformers use multi-head attention, where the process is repeated multiple times with different learned parameters, allowing the model to capture diverse relationships across the sequence. Section 3. Positional encoding, giving order to chaos. Wait a second. Since transformers don't process text sequentially, how do they understand word order? That's where positional encoding comes in. This technique adds information about each word's position in the sequence to its embedding. The original paper used sine and cosine functions of different frequencies to encode positions, ensuring the model could extrapolate to sequences longer than seen during training. For example, the positional encoding for position I and dimension d is defined as: for even d, sin I/10,000 2d/d. For odd d, cos I/10,000 2d/d. This creates a unique, continuous representation of position that the model can learn to interpret. Section 4. The encoder-decoder architecture. Transformers are built on an encoder-decoder framework. The encoder processes the input sequence, transforming it into a series of hidden states. The decoder then generates the output sequence, using the encoder's outputs to inform its predictions. Each encoder and decoder layer contains 2 sublayers, the self-attention mechanism and a fully connected feed-forward network. These sublayers are followed by residual connections and layer normalization, which stabilize training and improve gradient flow. But here's the kicker. The decoder also uses masked self-attention during training, ensuring it only attends to previous tokens in the target sequence. This prevents the model from cheating by peeking at future words. Section 5. Practical implications and beyond. The impact of transformers is everywhere. From language translation to code generation, these models have redefined what's possible. But the research didn't stop in 2017. Variants like BERT, bidirectional transformers, and GPT, generative pre-trained transformers, have pushed the boundaries further, introducing techniques like masked language modeling and causal language modeling. Today, researchers are exploring efficient variants like distill BERT and tiny BERT, which compress large models without sacrificing performance. Others are experimenting with vision transformers, applying the same principles to image recognition. The future: a world where transformers power everything from medical diagnostics to real-time language translation, without the limitations of their predecessors. Closing narration. Transformers aren't just a technical achievement, they're a paradigm shift. By reimagining how models process information, they've opened doors to new possibilities in AI. If you're inspired to dive deeper, check the description for links to the original paper, tutorials, and cutting-edge research. Thanks for watching, and remember, the next big breakthrough in AI might just be a few equations away.